Mixed oxide fuel, commonly referred to as MOX fuel, is nuclear fuel that contains more than one oxide of fissile material, usually consisting of plutonium blended with natural uranium, reprocessed uranium, or depleted uranium. MOX fuel is an alternative to the low-enriched uranium fuel used in the light water reactors that predominate nuclear power generation. For example, a mixture of 7% plutonium and 93% natural uranium reacts similarly, although not identically, to LEU fuel. MOX usually consists of two phases, UO2 and PuO2, and/or a single-phase solid solution O2. The content of PuO2 may vary from 1.5 Wt% to 25 €30 Wt% depending on the type of nuclear reactor. Although MOX fuel can be used in thermal reactors to provide energy, efficient fission of plutonium and MOX can only be achieved in fast reactors. One attraction of MOX fuel is that it is a way of utilizing surplus weapons-grade plutonium, an alternative to storage of surplus plutonium, which would need to be secured against the risk of theft for use in nuclear weapons. On the other hand, some studies warn that normalizing the global commercial use of MOX fuel and the associated expansion of nuclear reprocessing will increase, rather than reduce, the risk of nuclear proliferation, by encouraging increased separation of plutonium from spent fuel in the civil nuclear fuel cycle. Overview: in every uranium-based nuclear reactor core there is both fission of uranium isotopes such as uranium-235, 235, 92U, and the formation of new, heavier isotopes due to neutron capture, primarily by uranium-238, 238, 92U. Most of the fuel mass in a reactor is 238, 92U. By neutron capture and two successive beta decays, 238, 92U becomes plutonium-239, 239, 94Pu, which, by successive neutron capture, becomes plutonium-240, 240, 94Pu, plutonium-241, 241, 94Pu, plutonium-242, 242, 94Pu, and other transuranic or actinide nuclides. 239, 94Pu and 241, 94Pu are fissile, like 235, 92U. Small quantities of uranium-236, 236, 92U, neptunium-237, 237, 93Np, and plutonium-238, 238, 94Pu, are formed similarly from 235, 92U. Normally, with the fuel being changed every 3 years or so, most of the 239, 94Pu is burned in the reactor. It behaves like 235, 92U, with a slightly higher cross-section for fission, and its fission releases a similar amount of energy. Typically about 1% of the spent fuel discharged from a reactor is plutonium, and some 2/3 of the plutonium is 239, 94Pu. Worldwide, almost 100 tons of plutonium and spent fuel arises each year. A single recycling of plutonium increases the energy derived from the original uranium by some 12%, and if the 235, 92U is also recycled by re-enrichment, this becomes about 20%. With additional recycling, the percentage of fissile nuclides in the mix decreases and even neutron-absorbing nuclides increase, requiring the total plutonium and/or enriched uranium percentage to be increased. Today in thermal reactors, plutonium is only recycled once as MOX fuel. Spent MOX fuel, with a high proportion of minor actinides and even plutonium isotopes, is stored as waste. Existing nuclear reactors must be relicensed before MOX fuel can be introduced because using it changes the operating characteristics of a reactor, and the plant must be designed or adapted slightly to take it. For example, more control rods are needed. Often only a third to half of the fuel load is switched to MOX, but for more than 50% MOX loading, significant changes are necessary and a reactor needs to be designed accordingly. The Palo Verde Nuclear Generating Station near Phoenix, Arizona was designed for 100% MOX core compatibility but so far have always operated on fresh low-enriched uranium. In theory, the 3 Palo Verde reactors could use the MOX arising from 7 conventionally fueled reactors each year and would no longer require fresh uranium fuel. According to Atomic Energy of Canada Limited, CANDU reactors could use 100% MOX cores without physical modification. AECL reported to the United States National Academy of Sciences Committee on Plutonium Disposition that it has extensive experience in testing the use of MOX fuel containing from 0.5 to 3% plutonium. The content of unburned plutonium in spent MOX fuel from thermal reactors is significantly greater than 50% of the initial plutonium loading. However, during the burning of MOX the ratio of fissile isotopes to non-fissile drops from around 65% to 20%, depending on burn-up. This makes any attempt to recover the fissile isotopes difficult and any bulk PuO recovered would require such a high fraction of PuO in any second-generation MOX that it would be impractical. This means that such a spent fuel would be difficult to reprocess for further reuse of plutonium. Regular reprocessing of biphasic spent MOX is difficult because of the low solubility of PuO2 and nitric acid. Current applications. Reprocessing of commercial nuclear fuel to make MOX is done in the United Kingdom and France, and to a lesser extent in Russia, India and Japan. China plans to develop fast breeder reactors and reprocessing. Reprocessing of spent commercial reactor nuclear fuel is not permitted in the United States due to non-proliferation considerations. All of these nations have long had nuclear weapons from military-focused research reactor fuels except Japan. The United States is building a MOX plant at the Savannah River site in South Carolina. Although the Tennessee Valley Authority and Duke Energy expressed interest in using MOX reactor fuel from the conversion of weapons-grade plutonium, TVA said in April 2011 that it would delay a decision until it could see how MOX fuel performed in the nuclear accident at Fukushima Daiichi. Thermal reactors. About 30 thermal reactors in Europe are using MOX and an additional 20 have been licensed to do so. Most reactors use it as about 1/3 of their core, but some will accept up to 50% MOX assemblies. In France, EDF aims to have all its 900 MWE series of reactors running with at least 1/3 MOX. Japan aimed to have 1/3 of its reactors using MOX by 2010, and has approved construction of a new reactor with a complete fuel loading of MOX. Of the total nuclear fuel used today, MOX provides 2%. Licensing and safety issues of using MOX fuel include, as plutonium isotopes absorb more neutrons than uranium fuels, reactor control systems may need modification. MOX fuel tends to run hotter because of lower thermal conductivity, which may be an issue in some reactor designs. Fission gas release in MOX fuel assemblies may limit the maximum burn-up time of MOX fuel. About 30% of the plutonium originally loaded into MOX fuel is consumed by use in a thermal reactor. If 1/3 of the core fuel load is MOX and 2/3 uranium fuel, there is zero net gain of plutonium in the spent fuel. All plutonium isotopes are either fissile or fertile, although plutonium-242 needs to absorb 3 neutrons before becoming fissile curium-245. In thermal reactors, isotopic degradation limits the plutonium recycle potential. About 1% of spent nuclear fuel from current LWRs is plutonium, with approximate isotopic composition 52% 239, 94 PuO, 24% 240, 94 PuO, 15% 241, 94 PuO, 6% 242, 94 PuO and 2% 238, 94 PuO when the fuel is first removed from the reactor. Fast reactors, because the fission-to-capture ratio of neutron cross-section with high energy or fast neutrons changes to favor fission for almost all of the actinides, including 238, 92U, fast reactors can use all of them for fuel. All actinides, including TiU or transuranium actinides, can undergo neutron-induced fission with unmoderated or fast neutrons. A fast reactor is more efficient for using plutonium and higher actinides as fuel. Depending on how the reactor is fueled, it can either be used as a plutonium breeder or burner. These fast reactors are better suited for the transmutation of other actinides than are thermal reactors. Because thermal reactors use slow or moderated neutrons, the actinides that are not fissionable with thermal neutrons tend to absorb the neutrons instead of fissioning. This leads to buildup of heavier actinides and lowers the number of thermal neutrons available to continue the chain reaction. Fabrication: the first step is separating the plutonium from the remaining uranium and the fission products with other wastes. This is undertaken at a nuclear reprocessing plant. Dry mixing: MOX fuel can be made by grinding together uranium oxide and plutonium oxide before the mixed oxide is pressed into pellets, but this process has the disadvantage of forming lots of radioactive dust. MOX fuel, consisting of 7% plutonium mixed with depleted uranium, is equivalent to uranium oxide fuel enriched to about 4.5% 235-92U, assuming that the plutonium has about 65% 239-94 PuO. If weapons-grade plutonium were used, 90% 239-94 PuO, only about 5% plutonium would be needed in the mix. Co-precipitation: a mixture of uranyl nitrate and plutonium nitrate in nitric acid is converted by treatment with a base such as ammonia to form a mixture of ammonium diuranate and plutonium hydroxide. After heating in, a mixture of 5% hydrogen and 95% argon will form a mixture of uranium dioxide and plutonium dioxide. Using a base, the resulting powder can be run through a press and converted into green-colored pellets. The green pellet can then be sintered into mixed uranium and plutonium oxide pellet. While this second type of fuel is more homogeneous on the microscopic scale, it is possible to see plutonium-rich areas and plutonium-poor areas. It can be helpful to think of the solid as being like a salami. Americium content: plutonium from reprocessed fuel is usually fabricated into MOX as soon as possible to avoid problems with the decay of short-lived isotopes of plutonium. In particular, 241-94 PuO decays to americium-241, 241-95 Am, which is a gamma-ray emitter, giving rise to a potential occupational health hazard if the separated plutonium over 5 years old is used in a normal MOX plant. While 241-95 Am is a gamma emitter, most of the photons it emits are low in energy, so 1 ohm of lead, or thick glass on a glove box will give the operators a great deal of protection to their torsos. When working with large amounts of americium in a glove box, the potential exists for a high dose of radiation to be delivered to the hands. As a result, old reactor-grade plutonium can be difficult to use in a MOX fuel plant, as the 241-94 PuO it contains decays with a short 14.1-year half-life into more radioactive 241-95 Am, which makes the fuel difficult to handle in a production plant. Within about 5 years, typical reactor-grade plutonium would contain too much 241-95 Am, but it is possible to purify the plutonium bearing the americium by a chemical separation process. Even under the worst possible conditions, the americium-plutonium mixture will never be as radioactive as is spent fuel dissolution liquor, so it should be relatively straightforward to recover the plutonium by PuO or another aqueous reprocessing method. Also, 241-94 PuO is fissile while the isotopes of plutonium with even mass numbers are not, so decay of 241-94 PuO to 241-95 Am leaves plutonium with a lower proportion of isotopes usable as fuel, and a higher proportion of isotopes that simply capture neutrons. The decay of 238-94 PuO to 234-92U and subsequent removal of this uranium would have the opposite effect, but 238-94 PuO both has a longer half-life and is a smaller proportion of the spent nuclear fuel. 239-94 PuO, 240-94 PuO, and 242-94 PuO all have much longer half-lives so that decay is negligible. 244-94 PuO has an even longer half-life, but is unlikely to be formed by successive neutron capture because 243-94 94 PuO quickly decays with a half-life of 5 hours, giving 243.95 curium content. It is possible that both americium and curium could be added to a UO2 MOX fuel before it is loaded into a fast reactor. This is one means of transmutation. Work with curium is much harder than americium because curium is a neutron emitter. The MOX production line would need to be shielded with both lead and water to protect the workers. Also, the neutron irradiation of curium generates the higher actinides, such as californium, which increase the neutron dose associated with the used nuclear fuel. This has the potential to pollute the fuel cycle with strong neutron emitters. As a result, it is likely that curium will be excluded from most MOX fuels. Thorium MOX. MOX fuel containing thorium and plutonium oxides is also being tested. According to a Norwegian study, the coolant void reactivity of the thorium-plutonium fuel is negative for plutonium contents up to 21%, whereas the transition lies at 16% for MOX fuel. The authors concluded, thorium-plutonium fuel seems to offer some advantages over MOX fuel with regards to control rod and boron worths, CVR and plutonium consumption. See also. References. External links, technical aspects of the use of weapons plutonium as reactor fuel, synergistic nuclear fuel cycles of the future, nuclear issues briefing paper 42, burning weapons plutonium in CANDU reactors, program to turn plutonium bombs into fuel hits snags.